Guidance for inspectors on on-stream and off-stream inspection of reactors based on API 510 and API 572, inspection methods ensuring safety and compliance standards. Purpose and importance of reactor inspection, applicable codes and standards, API 510 and API 572. Inspection of reactors is a critical activity to ensure the continued safe operation, pressure containment integrity, and reliability of process units in the refining, petrochemical, and chemical industries. Reactors often operate under severe conditions, including high pressure, high temperature, corrosive environments, and cyclic loading, all of which can accelerate deterioration mechanisms. The primary purpose of inspection is to identify degradation before it leads to loss of containment, unplanned shutdowns, or catastrophic failure. From an inspector's perspective, reactor inspection provides assurance that the vessel remains fit for service throughout its intended operating life. It also supports compliance with regulatory requirements, company mechanical integrity programs, and industry-recognized standards. Inspections help validate corrosion rates, confirm minimum required thickness, and detect cracking, deformation, or damage to internals that could affect process performance. Effective inspection planning and execution also reduce risk by enabling timely repairs, optimized inspection intervals, and informed decisions regarding continued operation. Ultimately, a structured inspection program protects personnel, the environment, and assets while supporting reliable and profitable plant operation. API 510, Pressure Vessel Inspection Code, In-Service Inspection, Rating, Repair, and Alteration, establishes the minimum requirements for inspection intervals, inspection practices, evaluation, repair, and record-keeping for pressure vessels after they have been placed in service. It defines the roles and responsibilities of authorized inspectors and owner-users, and it provides guidance on thickness measurements, remaining life calculations, and acceptance criteria. API 572, Inspection of Pressure Vessels, complements API 510 by offering detailed guidance on how inspections should be carried out in the field. It describes common damage mechanisms, inspection techniques, and practical considerations for both external and internal inspections. Together, these standards form the primary technical basis for reactor inspection activities. Inspectors must also be aware of related references such as ASME Section 8 for construction rules and API 579/ASME FFS 1 for fitness for service evaluations when damage exceeds code limits. On-stream versus off-stream inspection philosophy, common damage mechanisms in reactors. On-stream and off-stream inspections serve different but complementary purposes within a comprehensive inspection program. On-stream inspection refers to examinations performed while the reactor is in operation. Its primary focus is early detection of deterioration through external visual checks, monitoring of operating conditions, and non-intrusive measurements such as ultrasonic thickness readings. On-stream inspections are essential for identifying abnormal trends, verifying assumptions used in corrosion rate calculations, and ensuring that the vessel remains within safe operating limits between shutdowns. Off-stream inspection, conducted during a planned shutdown, allows for a much more thorough examination. Internal access enables detailed visual inspection of the shell, heads, welds, and internals, as well as the application of a wider range of non-destructive examination techniques. Inspectors must understand the limitations and strengths of each approach and ensure that findings from on-stream monitoring are used to effectively plan the scope and focus of off-stream inspections. Reactors are susceptible to a variety of damage mechanisms depending on process conditions, materials of construction, and operating history. Common forms of damage include general and localized corrosion, erosion due to high-velocity flow or catalyst movement, and corrosion under insulation on externally insulated surfaces. High-temperature reactors may experience creep damage, characterized by bulging, distortion, or microcracking over long-term exposure. Cyclic operation can lead to fatigue cracking, particularly at weld toes and nozzles. Hydrogen-related damage mechanisms, such as hydrogen-induced cracking or high-temperature hydrogen attack, are critical concerns in hydrogen service. Stress corrosion cracking may occur in susceptible materials exposed to specific corrosive environments. Inspectors must be familiar with these mechanisms, understand where they are most likely to occur, and select appropriate inspection techniques to detect them effectively. Objectives and scope of on-stream inspection techniques and tools. The primary objective of on-stream inspection is to monitor the condition of the reactor while it remains in service and to identify signs of deterioration that could compromise safety or reliability before the next shutdown. Inspectors focus on external visual examination to detect leaks, corrosion, distortion, or abnormal vibration. Thickness measurements are taken at established thickness measurement locations to track corrosion rates and confirm remaining life calculations. Process data, such as temperature and pressure trends, are reviewed to identify excursions that could accelerate damage mechanisms. On-stream inspection also includes checking supports, nozzles, flanges, and bolted connections for signs of distress. While on-stream methods cannot replace internal inspection, they provide essential data for risk management and inspection planning. Typical on-stream inspection techniques include external visual inspection, ultrasonic thickness measurement, infrared thermography, and leak detection methods. Visual inspection focuses on identifying corrosion, coating breakdown, insulation damage, and signs of overheating. Ultrasonic testing is widely used to measure wall thickness at accessible locations without interrupting operation. Infrared thermography can help identify hot spots, refractory damage, or abnormal heat transfer patterns. Inspectors may also rely on process monitoring systems to detect pressure drops, temperature anomalies, or product contamination that could indicate internal damage. Proper documentation of findings and comparison with historical data are essential to identify trends and trigger further investigation if needed. Preparation and safety for internal inspection, internal visual and NDE inspection activities. Effective off-stream inspection begins with thorough preparation. The reactor must be properly isolated, depressurized, drained, cleaned, and gas-freed before entry. Inspectors must ensure that confined space entry permits, lockout, tagout procedures, and atmospheric testing requirements are strictly followed. Adequate lighting, access scaffolding, and ventilation are essential for a safe and effective inspection. Pre-inspection review of design data, previous inspection reports, corrosion rates, and known problem areas allows inspectors to focus their efforts on the most critical locations. Good preparation not only improves inspection quality but also reduces safety risks and inspection duration. Internal inspection allows direct assessment of the reactor's condition and is a cornerstone of API 510 and API 572 guidance. Inspectors visually examine the shell, heads, weld seams, and nozzles for corrosion, cracking, deformation, or evidence of overheating. Reactor internals such as catalyst support grids, trays, and hold-down devices are inspected for wear, distortion, and attachment integrity. During shutdowns, a broader range of non-destructive examination methods can be applied, including magnetic particle testing, liquid penetrant testing, ultrasonic flaw detection, and radiography where appropriate. Thickness measurements are verified and expanded as needed to refine corrosion rate calculations. All findings are documented in detail to support evaluation and future inspection planning. Assessment of inspection findings, fitness for service, and inspection intervalidation. After inspection activities are completed, inspectors must evaluate the findings against the acceptance criteria defined in API 510 and the original design code. Measured thicknesses are compared to the calculated minimum required thickness to determine remaining life. Detected flaws, such as cracks or areas of localized corrosion, are assessed for size, orientation, and growth potential. Operating history and future service conditions are considered to determine whether the damage is likely to progress. When inspection results indicate that code limits are exceeded or that uncertainty exists regarding continued safe operation, further engineering evaluation is required. Accurate assessment is essential to ensure that decisions are technically sound and defensible. When damage exceeds the direct acceptance limits of API 510, fitness for service assessments in accordance with API 579/ASME FFS 1 may be required. These assessments provide a structured methodology to evaluate whether a reactor can continue operating safely with known flaws or thinning. Depending on the complexity and severity of the damage, Level 1, Level 2, or Level 3 assessments may be performed. The results of inspection and evaluation are also used to establish or adjust inspection intervals. API 510 allows inspection intervals to be based on corrosion rates, remaining life, and risk-based inspection methodologies. Proper determination of intervals ensures adequate safety margins while avoiding unnecessary shutdowns. Inspection reporting and records, key takeaways for inspectors. Comprehensive documentation is a fundamental requirement of API 510. Inspection reports must clearly describe the scope of inspection, methods used, locations examined, and detailed findings. Thickness measurements, NDE results, photographs, and sketches should be included where applicable. The report should also document evaluations performed, remaining life calculations, and any recommendations for repair, monitoring, or changes to inspection intervals. Accurate and complete records support regulatory compliance, enable trend analysis, and provide critical input for future inspections and risk assessments. Maintaining high-quality inspection records is an essential responsibility of the inspector. Effective inspection of reactors requires a balanced approach that integrates on-stream monitoring with thorough off-stream internal inspection. Inspectors must understand the intent and requirements of API 510 and API 572, be knowledgeable about damage mechanisms, and apply appropriate inspection techniques. Careful evaluation of findings, supported by sound engineering judgment, is essential to ensure continued safe operation. By following a structured inspection process and maintaining accurate documentation, inspectors play a vital role in protecting personnel, assets, and the environment while supporting reliable plant operation.